Okay, so we're recording. So yeah, this is just review for this coming exam on Thursday. So just exam 3. So I'm not going to talk about chapters um 2, 3, or 4. This is just really going to focus on chapter 5.
I have a question.
Mm-hmm.
I was wondering if you could run me through what area we're approximating with Simpson's rule.
The area under the curve.
Well, I understand that it's the area of the curve, but you know how with our original integral, we're approximating it using rectangles, and then we're using trapezoids, and that's how we get those formulas for the sum. I was just wondering, like, what are we using to approximate in Simpson's rule?
Parabolic curves.
Parabolic curves. And
Yep.
how does the equation end up looking like that through parabolic?
You can look that up in the book.
Okay.
So it's not something that you're required to know how to do. So that's why I didn't really go over it. I don't think anyone really goes over it just because it's not that easy of a thing to go over. So it's just sort of a formula. You go, here you go. So I'm not going to require you to be able to derive it.
Okay.
Not at all.
Okay.
Because I got other stuff I need to ask you.
Yeah, that makes sense.
Okay. So Kevin.
Yeah, would you say, I mean, kind of the focus, or I guess, yeah, the focus I'm getting from this chapter, would you say this is going to be more of an equation heavy test, probably? Because that's kind of the feeling I'm getting from
You
everything
mean
we've
as far
done.
as like just like using formulas and stuff?
Yeah.
Yeah. So it's kind of like chapter 3. It's like you had to know all those derivative rules to be able to find the derivative. Well, now you have to know all the integration rules so you can integrate.
So should we, like like you were saying earlier, should we focus on like where it's derived from though, or the concepts behind it? Because with that chapter 3, there was a lot of questions involving like, oh, where did this concept come from? The limit, limits.
Um, not as much. Um, like even chapter 3, like it had some like kind of concept questions in there, but not as many as per se, or sorry, chapter 3, not as many as like there were in chapter 4. Chapter 4 there were a lot of concepts in there, whereas chapter 3 and chapter 5 not so much. Like you had a couple of theorems, but not like you did in chapter 4.
Okay. Sweet, thanks.
Mm-hmm. So let's do this. Let's go ahead and do you guys have any questions from the study guide? Because we can tackle that first, and then if you have any other questions from anywhere, we can hit those later. So do you have anything from the study guide? If you don't, that's totally fine too. Oh, let's see. 1N and 1P on the study guide. I will do my best to to look at the chat. But if for some reason, like you put a question in the chat and I'm not answering it, just ask out loud. Okay, so number 1N and number 1P. Okay, those are good. Okay, so when in the integral from 0 to 1 of x over 4 plus x squared dx. So anytime I encounter a fraction, I'm gonna see if it fits one of those LNs, because if it does, then I automatically have an answer. If it doesn't, then I can either tweak it a little bit so it fits an LN, or I'm gonna have to try and fit something else. So either like a U sub, an inverse trig function, something like that. So if you look at the denominator, 4 plus x squared, what's the derivative of 4 plus x squared?
Uh, 2x.
2x. And that's really close to what you have. You have the x, you're just missing the 2. So I'm gonna put the 2 in there so it matches the derivative that I need. Well, if I put a 2 on the inside, I have to put something else on the outside. What do I have to put out there? This is for anybody, like anybody can answer any question that's not for
1/2.
just the person asked. Yeah, a half, because you always have to put its reciprocal on the outside. And again, you can only do this with constants. You cannot do this with a variable. So you can't put in like an x on the inside and a 1 over x on the outside. It does not work that way. Okay, so the 1/2 you put out front stays. Well, now you have the derivative of that denominator sitting up top. So now it's an ln. And it's going to be ln of 4 plus x squared, and we're going from 0 to 1. So now you plug in your bounds. And if you're looking at your bounds, which number do you always plug in first?
The one from the bottom. Oh, no, the one on the top. So one, we would plug in one first, right?
Yeah.
Yeah.
Yeah. Yeah, it's always the upper bound, even if the numbers are out of order. So like if the upper bound is smaller, like it doesn't matter. You plug in the upper bounds first, no matter what.
Is that just the case because of the fundamental theorem of calculus? It just makes it a bit clearer if you do the first one and the second one.
Yeah, because it's f of b minus f of
Yeah.
a, not
Okay.
f of a minus f of b. So yeah, plug in the 1 first, then subtracting, plug in the 0. And then just simplify what you have. So that will be ln of 5 minus ln of 4. And you can leave your answer like this if you want to. That's totally fine. You can impress me with your knowledge of LNs if you choose to do so, which is not required, but you could change that into 1/2 ln of 5 over 4. So either of those two answers would be totally fine. Personally, I would stop at the answer that I boxed, because then you're done. But if you want to combine them into a single LN, you totally can.
So when we do the exam, you'd prefer us if we just do the one that you box, just leave it as the LN, not go like really in depth with it.
I don't have a preference. It's up to you. I would just stop at the one I boxed, because then I'm not doing another step and possibly making another error. So that's why I would stop there, but you can put either one.
Okay. Thank you.
Yeah. 1P. Okay, any other questions on 1n?
Could we also bring the 1/2 into the logarithm and then
You could,
the power?
yep,
Okay, but that seems a bit unnecessary though.
right. Because then you got to square root the 4, and yeah, you're doing all sorts of fun stuff after that. Okay, 1p. Okay, so the integral from 0 to 1 to x over 4 plus x squared squared. Okay, so if you do the same thing as we did in 1n, you'd be checking the denominator and trying to do the derivative of your entire denominator.
Professor, it's cubed.
It's cubed. Oh, it is. Okay, thank you. One second, let me zoom that in. There we go. Okay, so if you start to do the derivative of the entire denominator, you'd have to use the chain rule. So, pull the power down, decrease the power by 1, then multiply by the derivative of the inside. And you do end up with that 2x like you have in the numerator there, but you have all of this other stuff that you don't have in the numerator. So that ln trick isn't going to work for this one. So if it doesn't work, then you got to try some other techniques or other options. So you could try u sub. You could see if it fits an inverse tangent or an inverse trig. And see if it fits one of those, because you don't really have too many techniques. I know it seems like you do, but you really kind of don't. You have integrals that you can just integrate directly. Then you have u sub, then inverse trig, and then ln. So you really only have like 4 options. Clearly, it didn't integrate directly. It didn't work with the ln, so now it's one of the other 2. So for your inverse trig, it's not really fitting the format there either, because it has that power of 3 on the end on that quantity. So that's out. So u sub is the one to go with. So now you got to pick something for u. So what would be a good choice for you? And if
4
you
plus
don't know,
x
you
squared.
just have to try something. So say it again.
4 plus x squared.
4 plus x squared. And you'll know if it works or not, because the derivative of your u should be, oops, whatever's left in the integral. And in this case, it is. So the 4 plus x squared would take care of the denominator, and then the 2x dx would be taken care of by the du. So your denominator becomes u to the 3rd. The 2x dx becomes just du, or 1 du. And you can either leave it like that, or you can think of it as u to the negative 3rd. Either way, like you don't have to write u to the negative 3rd on your paper. But you are going to have to at least think it so you can integrate that. So what is the integral of 1 over u to the 3rd? or the integral of u to the negative third?
Is it -1/2 u to the negative second?
Yeah. And it's not going to be plus c because we have those original bounds. So you now have a choice. You can turn things back into x's and use the old bounds, or you could leave things in terms of u and get bounds that are in terms of u. And it doesn't matter which way you go, it just got to pick your favorite. So what do you guys want to do? Do you want to keep it the way it is and use new numbers, or do you want to switch it back in terms of x and use the old numbers?
I think the derivative's wrong for that, isn't it? For you? Wouldn't it be to the -4th since we subtract 1?
No, because we're not doing a derivative.
Oh, yeah, we're doing, oh, sorry, my bad, never mind.
So what do you guys want to do? Do you want to keep the old given bounds, or do you want to get new ones in terms of u?
Well, I think usually since we put it back to the old like x values, I say we should do the x values.
Okay, and that's totally fine. You get the same answer either way, so it really is your choice. Okay, so this -1/2, I'm going to leave it out front. So I'm going to plug in the 1. So that'll be 5 to the -2. Plug in the 0. So 4 to the -2. So wow, we have a fun time with that. So that becomes 1/25 minus 1/16. I'm running out of room. Okay, so your common denominator is 25 times 16, which would be what?
400.
400. And your numerator is basically 16 minus 25, so that's not bad. So that'd be negative. Be negative, all that fun arithmetic.
-9.
16 minus 25, yeah, that's usually -9. So 9/800. Okay, so you guys think you're okay with number 1N and number 1P?
Yes.
Okay. I'm gonna clear this out. Okay, somebody wants number 3. Number 3 is a fun one. And not because I'm the math teacher. So we're given that f of x is equal to the integral from 0 to x. of arc sine of root t. And they want to know what is the f prime of a fourth. So we need to take the derivative of that given f. So we're taking the derivative of the integral. So what rule are we really using without it having to tell us?
It's the second fundamental theorem.
Yeah, that's second fundamental theorem. And all it basically says is that what happens when you take the derivative of a definite integral?
You just swap out the variable, right? Or
Well, because what's happening? What's happening with the derivative and the integral? Like, what are they doing to each other?
reversing each other?
Okay, so they are essentially,
You're saying they're undoing each other?
yes, because
Sorry.
they're canceling each other out.
Right. Okay. Yeah.
So they're going to cancel each other out. So you are right. You do just replace the t with whatever that variable is, which in our case is just x. So it's just arc sine of root x. But they gave you a specific value to plug in for x. So you just have to take it a step further and then just evaluate it. So root it. And what's arc sine of a half?
Is it pi over 3 or pi over 6?
Well, it's one of them,
I think it's pi over 3.
not both. Maybe not that one.
Pi over 6 then.
Is it pi
Pi
over
over
6?
Yep, 30 degrees. If it was arc sine of root 3 over 2, that would give you the pi over 3.
Okay, that's not too bad. Thank you.
Somebody in the chat asked if we could do number 6.
Number 6.
Yes.
Okay, all right, at t equals 0, a particle starts at 6 feet and moves along the line in such a way that time t is, so that at time t, its acceleration is, okay. 24 t squared feet per second per second. So if the particle's velocity is 8 feet per second when t is 0, what is the position of the particle at t equals 2? Okay, so they gave us acceleration. They gave you the velocity. So v of 0 is 8. And then they gave us the position, or no, they want the position. Right, what is, yeah. Okay, so you need to know how position, velocity, and acceleration are all related to each other. So if we integrated acceleration, what does that normally give you?
Velocity.
Gives you velocity. Okay, so what is the integral of 24t squared?
So 8t cubed.
Yeah. And then your plus c. So we need to figure out what that c value is so that you can then get position from here. So that's where you're going to use that second piece of data. That v of 0 is equal to 8. So if you plug 0 in for t into the velocity, then it's going to knock that term out. And we get c is equal to 8. So now you have the exact, for that particular velocity function of 8 t to the third plus 8. But unfortunately, they don't want to know the velocity when t is 2. They want to know the position. So how do you get position from velocity?
You would need to integrate it again.
Yeah. So we're going to integrate 8t to the third plus 8. So what is the integral of 8t to the third plus 8?
Two t squared plus 8x.
Close. I like the 2 and the t, but not the power you gave. So it's not 2t squared, it would be 2t to
The 4?
the fourth. And then plus 8. And it wouldn't be an x, it would be
T.
it'd be a t. And then it's still plus, oh, whoops. It did give us another piece of data, I missed it. So at t equals 0, it says the particle starts at 6. So when when time is 0, you know the position is 6. So do the same thing we did before, plug in t equals 0 into position. Set it equal to 6, and then you should be able to solve for c, and this one that's not too bad. So c is 6. So now you have your particular function for position. So 2t to the fourth plus 8t plus 6. And now you can plug in t equals 2 and get that position there. As long as you do the arithmetic right. Okay, so what's 2 to the fourth?
64.
No,
16.
16. 16 times 2,
32.
32. 8 times 2,
16.
okay, 16 plus 32.
48.
48 plus 6,
54.
54. And because they gave you units in the problem, then you should give units in the answer. So it's like 54 or what?
Oh wait. feet per second.
Close.
Feet per second
That's a
per second.
velocity. That-
Oh,
nope,
never mind.
That's an acceleration. So
So
your only other choice,
just seconds. Oh.
Feet.
Oh.
All right, nice job with this one. So the process is the same no matter what the function is. So whether acceleration is a polynomial, a trig function, whatever, you're still gonna, if you are starting with acceleration and they want position, you do have to integrate it twice. If they want velocity, you only have to integrate once. I'm gonna try to help you remember, like, am I doing a derivative or am I doing an integral? I always thought of it like this. Like I have position, velocity, and acceleration. Typically, position is the higher is the function with the higher power in it. So to me, it's like the highest or the largest function. So if I'm going to work my way down to acceleration, I'm doing derivatives. But if I'm going to work my way back up, so starting with acceleration and going up to position, I'm going to have to integrate. If you have velocity and they want acceleration and they also want position, you're going to have to do one of each. Because you got to go down or do a derivative to get acceleration. And then you're going to have to integrate to go up to position.
That's actually a pretty good way of looking at it.
Like, I liked it, but like that's, yeah, sometimes it's just me.
Are we allowed to ask more questions?
Oh, I guess.
Oh, okay.
Sure. What do you
Can
have?
we do number 7? I was a little bit confused on that one.
It's from the study guide still?
Yes, from the study guide still.
Okay, so number 7. Okay, so G, it's a twice differentiable function. What does that mean? If they say it's twice differentiable, what the heck are they talking about?
Oh gosh, I'm being put on the spot.
Well, it's anybody, not just for Sean.
It means it's continuous.
It does, but um, what else would it imply? It's like, yeah, it's continuous, but they would have said it's, I mean, that's kind of inherent to a differentiable function in the first place.
And it can be integrated.
Not that it can be integrated. Twice differentiable means that that the first and the second derivative would exist. So in other words, you could do a derivative twice, like right in a row, and you'd be able to find a second derivative. So that's all that's telling you. If it was thrice differentiable, that means you could find 3 derivatives, and so on and so forth. Okay, so with this, you could get the first and the second derivative. So what is the first derivative? So in other words, what's G prime? And what little theorem would we be using to find it?
Would G prime be the antiderivative? Or the derivative, I mean.
It's kind of both.
Is it just f of t?
Close. Not f of t, but
f of x.
f of x. Because what
The
theorem?
second fundamental theorem of calculus.
Yeah, that second fundamental theorem. Because again, you're doing a derivative of a definite integral. And according to the theorem, it says, well, you're going to get the same function, but it's now just in terms of that bound, or in this case, in terms of x. So you don't have to do anything fancy. You're just replacing, in this case, the t with an x. And that's all it is. So it's basically the same question as number 3, or it's the same concept. A derivative will cancel out a definite integral every single time. Okay, so if G prime is equal to F, what's G double prime equal to?
So just f prime.
Yeah, just the derivative of F. Like if you knew what f of x was, you could give me a very specific derivative, but you don't. So all you can do is just use the derivative notation. Now, it didn't ask for this, but if it did, what's the third derivative of G equal to?
F double prime
Yeah,
of x.
yeah. And if it asked for the fourth derivative of G, that would equal,
F triple prime.
yeah. So I mean, you're just going down the line. And just listing them out.
Mm.
So again, didn't ask for those last two, but I think you got it. Okay, so part C, G of X is increasing when F of X is doing what? So you do kind of have to think about what we did in chapter 4. If you want to know where a function is increasing, you were looking at its what?
Its sign.
Not of that function, not of the original. You were looking at the sign of
F of x.
the
Oh,
the derivative,
oh, the derivative. Okay.
right? If you want to know where a function is increasing, you look at its derivative. Same for decreasing. Well, what's the derivative of G?
F of x.
Yeah, f of x. So it's increasing when the derivative of G or F is either positive or negative. So which of the two?
Positive.
Because if the derivative is positive, that means the original function is increasing. So then for D, G is decreasing when the derivative or F is what was it?
Negative.
Yeah, just negative. Okay, so then for E, G is concave up when the second derivative of G or the first derivative of F, because they're equal, is
Is that increasing?
not increasing. Like you,
Decreasing? I
nope,
always mess these up.
Negative, if it's negative? Or
yeah, concavity is going off the second derivative, right?
Mhm.
So if it's gonna be concave up, the second derivative has to be
Negative.
positive,
Oh, positive.
but we know the second derivative of G is equal to the first derivative of F. It has to be positive. So then for part F, G is concave down when its second derivative is
Negative.
negative.
I had a hard time with these in chapter 4.
Yeah, not gonna lie.
Real hard time.
Yeah, they you know, they can take a while to kind of wrap your brain around it and like, oh, okay. It takes a minute. Not always, but from most of it, it kind of does. Okay. Any other questions on number 7?
No, you explained it perfectly. Thank you a lot.
Okay, you're welcome. Okay, someone else is asking number 5. Okay, so water is leaking from a tank at a rate modeled by where R is differentiable and decreasing from 0 to 8. Selected values are shown in the table above. Okay, so then we're running through all of those.
You could just do 5A if you didn't want to do B through D.
Somebody wants me to do B, C, and D as
Oh,
well.
sorry.
So, okay. So set up but do not evaluate an expression involving a definite interval that gives the amount of water that has leaked from the tank during the 8 hours. Okay, so we know you're gonna have a definite interval since it told you. So we're gonna put one in there. And you should also know what the bounds are. Like, what are the bounds?
For this part of the question,
Mhm.
would it be 0 to 8 since it's asking
Yeah.
for all 8 hours? Okay.
Yep. So 0 to 8. Okay, so we need to have a function that goes in there. So what's your function?
Oh,
This is what I wasn't sure about.
Well, what's the only function that they talk about? I'll give you a hint. It's not something specific. It's kind of like how we were just working in number 7. Like with F and G. So in this case, it would be
R of T.
R of T. That's the only function you have. You just don't know what it equals exactly, but you just know it's function. And then DT. And there you go. So that's part A. So you can't evaluate it because you don't know what the function is. But you weren't supposed to evaluate anyway, just how to set it up. So parts B, C, and D is where you're kind of trying to evaluate it, but the best you can do is just an approximation. And so they're having you run through those rules to just approximate it. So part B, it's the right Riemann sum. And you're using the data in the table to do it. So the left and the right Riemann sums, those were using the rectangles. So your first rectangle is going from 0 to 1. Your second is from 1 to 3. Third would be 3 to 6. And then your fourth would go from 6 to 8. So on that first rectangle, from 0 to 1, what's the width of that base? So in other
1.
words, yeah, what's the distance from 0 to 1? That would be 1. And then for the height, you have two function values there, the 1340 and the 1190. So you need to choose the value that is physically typed there on the right. So which of those two numbers is physically on that page on the right?
1190.
The 1190. Okay, so then the rest of them were pretty much, or pretty similar. So the next rectangle goes from 1 to 3. So that base would be
2.
2, because that's the distance from 1 to 3. And then you're choosing the function value that is on the right.
So 950.
That'd be the 950. And then the rectangle from 3 to 6, the base would be 3. And then the number on the, or the function value on the right side would be your 740. And then the last rectangle from 6 to 8, the base is 2. And then the function value on the right would be 700. So then to finish it, you would just multiply and then just add everything up. So I'll let you guys do that part. Okay, so part C is the same thing, but now you're doing a left Riemann sum as opposed to a right. So the base of every single one of those rectangles should be exactly the same. It's the function values that are going to be different. Because now you're choosing the function value on the left side as opposed to the right. So some of those function values are going to repeat, but not all of them. So like for your first rectangle, when you're looking at 1340 and 1190, which of the two function values are on the left?
1340.
Yeah. And then you look at the function values on the second rectangle, the 1190 and the 950. Well, the one on the left is your 1190. So now they're going to start to repeat. But the last function value to choose would be your 740, since that's the one on the left. Okay, so does that make sense as to like which function values go where?
Yes.
Okay,
I have a quick question though. like I know it's not actually on the study guide itself, but if we had to, if for example, if we had a problem that had to use like midpoint Riemann sum, so
Mhm.
for this example, would we, if it was like, for example, like from 0 to 3, we would just use 1, correct?
0 to 3. Right. If that, you're talking about like if that was your rectangle from 0 to
Yes.
3.
Yeah.
Yeah. Hmm.
Okay.
Yeah. If I did ask for a midpoint, like he's got it right as far as the concept, but your the the midpoint would really be in the middle between those two values. So
Mm-hmm.
it wouldn't be off center. Like 1 is not in the middle from 1 to 3. Like it should be
Oh
like
yeah.
1 to 5. So it would make sense based on the table. Like things aren't going to be like offset in a weird way.
Mm-hmm.
Okay, and then D, the trapezoidal. Okay. So the trapezoidal, you're using the area of a trapezoid. And the area of a trapezoid is
1/2 times the base.
close times the height. And then that's multiplied to the sum of the two bases.
Yeah.
Okay. Okay, so you're still using that same table. So your first trapezoid is going from 0 to 1. So your height, so for trapezoids, the height is actually the horizontal distance and the vertical are the bases. So from 0 to 1, your height's going to equal 1. And then for the bases, now you're not deciding, well, is it 1340 or is it 1190? It's both of them because you have to add them together. Okay, and then it's the same thing all the way down. So from 1 to 3, your height is 2. And then you're adding 1190 and 950. The third trapezoid from 3 to 6, so height is 3. Bases are 950 and 740. And then the last trapezoid from 6 to 8 has a base or a height of 2. And then the base is 740 and 700. So again, you would just do the arithmetic on that and just get a total. Yeah, it's not too bad with a table. It's actually kind of nicer with the table because you don't have to calculate the function values, they just give them to you. So as long as you choose the right one, you're usually good to go.
So for this one, would the answer be like, I think it's 7,380, somewhere around that?
Sure, where are they? Yeah. So for B, it was 6710. Oops.
Hmm.
The left one was 80-50. And the last one was 73-80. Oh, somebody else asked if this was going to be posted to my YouTube channel, and the answer is yes. All right, do you have any other questions from the study guide?
If we have time, I'm just confused on how to graph number 10.
Okay. The rest of it's good.
Yeah, the rest is good. I haven't solved it yet, like in the actual study guide, I haven't reached that point, but like even since before, like on the homework, I kind of struggled with drawing the graphs out. So
Okay, so y is equal to cosine of x. Y equals 0, x is equal to 0. And x is equal to pi over 2. Okay, so cosine of x. You know, that's just your standard cosine graph. So it starts up at the top and then goes like that forever and ever and in both directions. But we're specifically bounded by those other three equations, the y equals 0, x equals 0, and x equals pi over 2. So y equals 0, that's just the x-axis. X equals 0 is the y-axis. And then x equals pi over 2. That could be, like, they could give that anywhere along that curve, but pi over 2 specifically is your first x-intercept. So this would be region R. And it hits the y-axis at 1. So that would be part A, so that would be your graph. Part B, you're just going to integrate it from where to where?
Zero to pi over 2.
0 to pi over 2, going off the x values. So the integral of cosine of sine. Plug those values in. And then just evaluate them. So the area of region R is 1. Okay, then for C, the line x equals k divides the region into 2 equal halves. Find the value of k. So essentially, it's taking that curve and it's splitting it in half. You just don't know what that value is. But you know its area going from like 0 to k. Like if you just integrated from 0 to k and found this area in here, what does that have to equal as a value? Like what's that area total?
Half.
A half. Because it's half of the full area of R. So if the whole area was 4, then half of it would be 2. If the whole area was 6, then half would be 3. If the whole area was 5, then half would be 5/2, and so on and so forth. So you don't know what the value of k is, but you know that the whole thing is going to equal a half. So just integrate the left side, plug in your bounds. Still equal to a half. Sine of 0 is 0. And now you're solving for where sine of k is equal to a half. So where does sine equal a half?
Pi/6.
Where's the second value?
And 7 pi/6.
No,
Oh, that's no.
that was a
Sorry,
little too
5
far.
5 pi/6.
There you go. Yeah, but because you're only looking from 0 to pi/2, you can get rid of this one and you're only left with this one. All right, any questions on number 10?
No, thank you so much.
Mhm. Okay, number 8. Ooh, that's a good one too.
While you're writing that, I have a quick question. Will you also be doing like another one of these like Zoom meetings for our final exam?
Probably not.
Hmm.
The only reason why I was doing it this time is because my in-person class didn't have a meeting at all this last week because of Thanksgiving. So I didn't see them for 2 full weeks.
Mm-hmm.
So I couldn't review with them really at all. So that's kind of why this is here. So I figure, well, I'm reviewing for the in-person one. Online can join us as well.
Thank you.
Sure. Okay, so the absolute value of x over x. You can't really integrate it that well. Like we never went over a formula for it. Which means that if you actually integrated it and told me what the result was, you're using something to tell you what that integral was, and that's something you shouldn't be looking at. So if you don't know how to integrate this, like we've never done this at all, then you're forced to use something else. So you have to kind of go back to what a definite integral represents. Like, what does a definite integral represent?
Is it an area?
It's the area under the curve. So if you can't integrate this with any known technique, your only other option is to graph it and get the area from -1 to 2 for this one. So the absolute value of x over x, like we've done it before, it's just been a long time. And if you don't know what the graph is, you can just start making a table of values. So you can't plug in 0, then make it undefined. But if x is 1, if you plug that into the function, what do you get as an answer? This is for anybody. So if you plugged 1 into both of those x's, what do you get as a result?
1.
Yeah. What about if you plugged in x equals 2? Does it look like
It's 1.
this? Yeah, that's also gonna equal 1. If x is 3,
1.
x is 50,
1.
yeah. Well, what if you plugged in -1?
It's -1.
Yeah, that's gonna give you a -1. If you plugged in -4,
-4.
negative,
Sorry, -1.
-1. If you plugged in -1,000, that's also gonna give you -1. So if it's anything larger than 0, it's 1. If it's anything smaller than 0, it's -1. So your graph is a horizontal line out to the right at 1, and then a horizontal line out to the left at -1. So we're looking for the area under the curve from x equals -1 to x equals 2. So that would be this area. And that area. Which is kind of nice because now it's just the area of what shape?
Rectangle.
Yeah, just rectangles. So on the first rectangle, the one that's below the x-axis, the base is 1 and the height is 1. And then for the area above the x-axis, the base is 2. And its height is also just 1. But the area above the x-axis is positive, and the area that's below the x-axis is going to be
Negative.
negative. So any area below your x-axis is going to be a negative. So -1 plus 2,
1.
1. Okay, so there's a quick question from the notes of 5.5.
Can I share my screen to ask it?
Sure.
Because it's from the notes, but I don't know how I'm gonna like show it to you without sharing screen.
Okay. Actually, let's see. 5.5.
Yeah, it's on page 9.
Okay. Okay. Which one?
So my question was for like picking the U on example D, we picked the angle, which was 4 theta, but on example F, we picked the entire trig function, so sine. And
Right.
I'm just confused on when I would pick the angle or when I would pick the entire function.
You typically pick the angle when there's a coefficient with it. So like in D, your angle was 4 theta, and in example F, it was just theta.
Okay.
So like, for example, F. Let's just say you went, oh, let's pick the angle for the U. So the du would be d theta, and then everything would turn into this sine squared u cosine u du. And all you did is just replace the theta with the u and it didn't help you.
Yeah,
Whereas in example D, if you choose it to be the angle, now it will help you because your 4 d theta becomes du. And your 4 theta becomes just u. So in example D, now you can integrate it. So just tangent. And then change it back. Whereas back in example F, like if you just choose the angle and nothing happens, like you're still in the exact same position as you were before, it's just with a u instead of theta. So you didn't really help yourself. So sometimes when there's multiple trig functions like that, that's another indicator that, oh, I think my u is going to be an actual trig function as opposed to just the angle.
okay. So I could make my U like whatever I want depending on the problem.
Yeah, as long as it works, like you have your everything accounted for. Yeah,
So if I had like 1 plus 4x, I could make that into my U for a problem.
like if it was,
Like a polynomial, like I could use that for a U.
like if you had this,
Yeah, but like I needed to make that my U. Could I make that entire function a U? And then my DU would just be 4.
yeah. So if you had it like 4 over that, then yeah, I would totally choose that for my u.
Okay. Yeah, that
And
answered
then-
my question.
Yeah. All right, what else do you guys want to talk about? So we have about 10 minutes.
If no one has anything else, could we do number 2 from the study guide?
Oops, I can get back to it. Oh, the average value, okay. Okay, find the average value of the function over the given interval. So average value has a real specific formula. Remember what that was?
It's the 1 over b minus a,
Mm-hmm.
and then the integral with the bounds of the function.
Yeah. Okay, so we're going from 0 to 2. So b is 2, a is 0. And the function is x e to the x squared. So when you're going through and like trying to figure out how to integrate it, you have 4 options. The first one is directly. Like you can just integrate it just by looking at it. Like you can integrate like x or sine of x, something like that. So then it's pretty simple. Second option would be is it fitting an ln. Third, inverse trig. And then the fourth is a u sub. And it doesn't have to be in this order. Those are just your 4 options to choose from. So you can't integrate it directly. It's not an ln because there's no denominator. It's not an inverse trig for the same reason. So U sub is gonna be the one to go with. So what would be a good choice for you? And with ease, it was pretty specific usually as to what the choice for you was.
It's supposed to be the exponent for ease, correct?
Yeah,
So would you,
like
oh,
equal
x squared.
Yeah. So then your du would be 2x dx.
Oh, I see.
Excuse me. So you need a 2 on the inside and a 1/2 on the outside, even though you already have a 1/2 out there. That's not from the U sub, that was from the average value formula. So that original 1/2 that's sitting out in front in red is still there. So a 1/2 times a 1/2 is just a 1/4. And now you're going to integrate e to the u du. And for this one, I think the last time we had a problem like this with a u sub, we changed everything back into terms of x. So I'll do it differently this time. Instead of doing that, I'll get new bounds. So when x is 2, what would u equal? And that's using this thing right here.
Four.
Yeah. So that's my upper bound. And when x is equal to 0, u is also going to equal 0. So that's my lower bound. So now you can just integrate and just get e to the u, and then you can use the new bounds of 0 and 4 without having to change it back into terms of x. You can totally change it back into x and use 0 and 2 if you wanted. You'll still get the same exact answer. So stick in the 4, stick in the 0. And the only other thing I would really do is simplify e to the 0 as 1. You could distribute the 1/4 if you wanted. You could leave it out, either way.
And if you were to go back into terms of x, the u would just stay the same, right? Because it's an e.
So if
Or
you
do
went back
you,
in terms of x, like if you'd integrate it, and it would look like that, 1/4 e to the u,
right?
and then you would change it back into e to the x squared,
Okay, right.
going from 0 to 2. So you'd stick in the 2. So 2 squared gives you 4. Stick in the 0. 0 squared is 0. So you end up with the exact same thing. You just change it back into x. So I don't care which way you go, it's your choice. So just pick your favorite.
Thank you.
You're welcome. All right. I think I've got time for one more if you've got one.
If no one else has any, since we're on like the study guide anyways, we might as well just do 9. If there's time for 9.
I do number 9. Oh no, I do not. Okay. Okay, which of the following properties are true? Okay, so the integral from A to B of K f of x dx. They said it's equal to K times the integral from A to B of f of x dx. So do you think that's true or false? We also know K is a constant.
That's true.
That is true. You can always pull a constant out in front of the integral, but you can't do that with a variable. Okay, so the first one is true. So the second one,
That's exactly what they did.
yeah, they pulled the variable out. So are you allowed to do that?
Yes.
No.
Oh.
That's what we just said. You can only do that for a constant. You can't do that with a variable. It's people do it because it would be really nice if you could, but you can't. So you can only pull out a constant, like a number. You can't pull out a letter like that. A letter that's a variable. Okay, so the second one's out. Choice number 3. Looks like they're splitting. We're trying to split the integral up. So from A to C, plus from C to B, where C is in between A and C, or A and B. So are you allowed to bust apart a definite integral like that?
Yes.
Yes.
Why is it so, like, why is it allowed that we're able to do that?
That's the property. Like we used it before. Remember when we did the area of those two rectangles?
Yeah.
That's what you did, right? You took the area from -1 to 0 and then did the area from 0 to 2. You split it. So definite integrals, you're allowed to split as long as this number is in between the two of them. If it's not, then no, you can't do it. But as long as it's somewhere in there, you're totally allowed to split it.
Isn't that one of our rules or like theorems? Or
Yep.
Okay.
Yeah, it's one of your properties, which is the first and the third one are they're each a property. I forget what page that's on.
It's 5.3, page 16. I just found it.
Okay. Yeah, I was like, I think it's in 5.3 and it was on page 16.
Yes.
Okay. There's another one in there too, but that wasn't one of your choices. So that would be choice C, 1 and 3 only.
All right.
Okay, well, not too bad. We got through most of them, or at least, well, definitely not most of them on number one, but we said a couple.
I mean, I would assume that we did the most, like, I guess, like the hardest ones. So, so I guess that's a burden off our shoulders.
It's like, I wouldn't say necessarily the hardest ones, because in number one, the reason why number one is there is to help you realize like, oh yeah, I really do have to know all my integration techniques, not just some. So that's why number one is there. And like, yeah, I have to know my formulas. And then the others are just there because they're going off of some concept or some property or something that's important.
Very much true.
Yeah,
Very much true.
whatever it's in. All right, well, that's all the time we've got for today. But you can always send me your questions too.
Thank you.
All right.
You're
Thank you so
welcome.
much. Thank you for taking the time out of your day to help us out.
Sure. All right, so once the video renders, I can post it to my YouTube channel. So sometime either today or sorry, sometime this afternoon or later this evening, it should be up there somewhere. And it should be under, I think there's already a playlist from like 400 review sessions. So it should be in there with the correct semester and year. You can look at the other ones too, but at least this one will be specific to what we talked about today.